Let's take a look at this example. This time we have given voltage across the inductor, voltage across the capacitor, and also we have given voltage across the resistor and current. And this is series circuit. You're supposed to remember that in series circuit, the current which goes through each component is equal to the current total. So I can say that I total is equal IR, this is also equal IL, and this is also equal IC. And at this particular problem, this current is equal 50 milliamps. Please notice that this current has no angle. So we can say that this value is not complete yet, but we are going to find the angle soon. Now, we have to find the resistance, inductive reactance, and capacitive reactance, and Z total. So in order to do so, I'm going to use Ohm's law. Keep in mind that resistance is equal voltage across the resistor divided by the current which goes through the resistor. So voltage across the resistor is equal 40 volts, and the current which goes through the resistor we said is equal 50 milliamps. This is equal 800 ohms. Okay, so this is the value of the resistor in my series circuit. Next, I'm supposed to find X of L. X of L is equal voltage across the inductor over the current which goes through the inductor. So I have VL is equal 20 volts divided by IL, which is also equal 50 milliamps. This is equal 400 ohms and angle of 90 degrees. Keep in mind that anytime you write value of the inductive reactance, you're supposed to write always angle 90 degrees, or if you want to express this answer in rectangular form, you're supposed to write J 400 ohms. Either way is correct. Next, we're supposed to find X of C. X of C is equal VC over the current which goes through the capacitor. So voltage across the capacitor is given as value 100 volts over IC, which is equal 50 milliamps. This is equal 2 kiloohms and angle of negative 90 degrees. Again, keep in mind that we are talking about the capacitive reactance. Capacitive reactance goes always with angle negative 90 degrees, or we can also write in rectangular form negative J 2 kiloohms. Now we are ready to find Z total. Because this is series circuit, I'm supposed to add all these three impedances together. So I have Z total is equal resistance plus X of L plus X of C, where resistance we found is equal 800 ohms plus X of L, which is equal 400 ohms and angle of 90 degrees, plus X of C is equal 2 kiloohms and angle of negative 90 degrees. This is equal 1.78 kiloohms and angle of negative 63.43 degrees. So this is the total impedance of my circuit, series circuit. Next, the problem is asking me to find the inductance. In order to do so, I'm supposed to write the formula for the inductive reactance. X of L is equal omega L. Because I'm looking for inductance, I'm going to ignore the angle and let's say J if you want to talk about the rectangular form. Okay, so if you're looking for For inductance, you're not supposed to include angle or J. So solve this formula for L, and you're supposed to obtain L is equal X of L over omega, which is equal X of L we found 400 ohms divided by omega, which is given and has value 5 times 10 to the 5th radians per second, is equal 800 microhenries. So this is the inductance in my series circuit. Next, we're supposed to find the capacitance in the series circuit. In order to do so, I'm supposed to use the formula for the capacitive reactance. X of C is equal 1 over omega C. Again, if you're looking for C, you can ignore the angle or J. Okay, you're not supposed to use them. So solve this formula for C. C is equal 1 divided by omega X of C. So this is equal 1 divided by omega 5 times 10 to the 5th times X of C, which is equal 2 coulombs. This is equal 1 nanofarad. Okay, so this is the capacitance in my series circuit. Next, we're supposed to find the true power. Okay, in order to find the true power, I'm going to write the formula true power is equal IR squared times resistance. Why I'm using this formula? Because this problem is not saying that I'm supposed to use peak values of voltages or current, so automatically I assume that this is RMS. If your professor, or let's say the book specify that, let's say it has to be peak value, supposed to use 1/2, but if it doesn't say anything, most of the time this is going to be RMS. So true power is equal the current which goes through the resistor, 50 milliamps raised to the second power times the resistance, which is equal 800 ohms. Everything is equal to watts. Okay, so this is the true power in my series circuit. Now, we are going to find the reactive power in the series circuit. Before I'm going to write the formula for the reactive power, I'm going to find the total reactance in the circuit. So I have XT is equal X of L plus X of C. X of L we found is equal 400 ohms, an angle of 90 degrees, plus X of C, which is equal 2 kiloohms, an angle of negative 90 degrees. Everything is equal 1.6 kiloohms, an angle of negative 90 degrees. So the total reactance in my series circuit is equal 1.6 kilo, an angle of negative 90 degrees. So Q is equal I total square times X of T. This is equal 50 milliamps raised to the second power times 1.6 kiloohms. this is equal 4 volt ampere reactive. Next, we're supposed to find the apparent power. Apparent power, S, is equal I total raised to the second power times Z total. So this is equal 50 milliamps raised to the second power times Z total, 1.78 kiloohms. Everything is equal 4.45 volt ampere. Now we are ready to find the power factor. Power factor is equal cosine of angle theta, angle which is next to Z total. So I have cosine of the angle negative 63.43 degrees. This is equal 0.447 lead. Okay, so this is the angle which I have next to Z total, and because I have negative sign, I'm supposed to use word lead next to the value of the power factor. Why? This is telling me that the current in the circuit leads the voltage source by angle of 63.43 degrees. Okay, so next we're supposed to find the parallel equivalent circuit. In order to do so, we're supposed to find Y total. Y total is equal 1 over Z total. Now I would like to ask you to switch your calculators to the rectangular mode in order to get the answer from this calculation in rectangular form. So I have 1 over Z total, we found is equal 1.78 kiloohms, and angle of negative 63.43 degrees. This is equal 251.28 microsiemens plus J 502.46 microsiemens, where the real part of my answer is conductance and imaginary part is my capacitive susceptance. So now we are ready to find the resistance in the parallel equivalent circuit and capacitive reactance. Okay, let me draw the diagram first. So I have resistor and I have capacitor. Okay, so I have R and this is my CP, this is my voltage source. So resistance in my parallel circuit is equal 1 over G. So I have 1 divided by 251.28 microsiemens, and this is equal 3.98 kiloohms. Okay, so this is the value of the resistor, and I can find XP, but at this moment we know that this is going to be capacitor, so that's why I'm going to write that XP is equal to X of C in my parallel circuit is equal 1 over BC. So if 1 over 502.46 microsiemens, this is going with the angle of 90 degrees, or we can say with J, because we have J, I'm going to include J over here. Don't forget about the parentheses. This is equal 1.99 kilo ohms and angle of negative 90 degrees. Now we are going to look for currents which go through the resistor in the parallel equivalent circuit and capacitor in the parallel equivalent circuit. In order to make the life a little bit simpler, I'm going to find the voltage source first. Keep in mind that we prefer to have the value of voltage source with angle equal 0. That's why I'm going to write that voltage source is equal I total times Z total. Okay, I'm going to use the current which was given at the beginning and the Z total for my series circuit. Please keep in mind that the total impedance of the series circuit and total impedance of the parallel circuit must be the same. So if I'm going to find voltage source for series circuit, the same voltage source is going to be also for the parallel circuit. So if I total equals 50 milliamps times Z total 1.78 kilo. Please notice that I didn't include the angle because I want to keep voltage source with angle of 0 degrees. So I have voltage source is equal 89 volts. So now we are ready to find the currents. IRP is equal voltage source over the resistance RP. 89 volts divided by 3.98 kilo ohms. This is equal 22.36 milliamps and angle of 0 degrees. So this is the current which will go through my resistor. Next I'm supposed to find the current. So if ICP is equal voltage source over X of CP. This is equal 89 volts over XCP is equal 1.99 kilo ohms and angle of negative 90 degrees. This is equal 44.72 milliamps and angle of 90 degrees. Next, we're supposed to find the capacitance of the capacitor in the parallel equivalent circuit. In order to do so, I'm going to use the formula for capacitive reactance. X of Cp is equal 1 over omega Cp. Solve this formula for Cp. So you'll have Cp equals 1 divided by omega times XCP. This is equal 1 divided by, open parenthesis, omega 5 times 10 to the 5th radians per second times XCP, and we found XCP equals 1.99 kilo ohms. This is equal 1 nanofarad. Okay, so this is the capacitance over here. So I have Cp equals 1 nanofarad and Rp is equal 3.98 kilo. Voltage source is equal 89 volts. So now we're supposed to find the true power in the parallel circuit and the reactive power. So true power is equal voltage source raised to the second power over resistance, where voltage source we found is equal 89 volts raised to the second power over RP, of course. RP is equal 3.98 kiloohms. This is equal 1.99 watts. And let's compare what we obtained from the previous calculations, which we did for the series circuit. So P was equal 2 watts. So we can say that these values are identical. They are very close to each other, so we can say that our calculations up to this moment are correct. So if you want to find QP, the power in my reactive power in my parallel circuit, we know already that this is capacitor. We can also say this is QC equals voltage source raised to the second power over X of CP, which is equal 89 volts raised to the second power over XCP, 1.99 kiloohms. This is equal 3.98 volt ampere reactive. Okay, so this is the reactive power in my parallel equivalent circuit, and let's compare with the reactive power which we got before. So I got Q equal 4 volt ampere reactive. So as you can see, these two values are very close to each other, so we can say that our calculations are okay. And I don't know if you realize that we've finished the problem.